Hi. Am I audible now?
Yes. You can start. Go ahead.
I hope it is visible.
Yes.
I'm Bhumika and Bhumika is Bidari. Currently working as a verification engineer. I'm here to train the Verilog. Today I'll be discussing about half adder and full adder and also mux. These are completely combinational, which means doesn't have any memory and also doesn't have any clock. So coming to half adder, what is a half adder? Half adder is nothing but performing addition of two numbers. For example, considering this, there are two inputs, A and B. For two inputs, we'll have four combinations. How do we decide that is? Two power n is equal to question mark. So let us consider 2 power. What is n? N is the number of variables. We have two inputs, that is A and B. A and B are the variables. So 2 power 2, there are two variables. 2 power 2 is 4. So this 4 represents the number of combinations. See, 0, 0, 0, 1, 1, 0, and 1, 1. And we have sum and carry both as output. Coming to sum. So here we are adding it. 0 plus 0 is 0, and the carry is 0. 0 plus 1 is 1, and the carry is 0. 1 plus 0 is 1, and the carry is 0. When we have 1 plus 1, we'll have it 0, and the carry is 1. Okay, because we can't take 1 plus 1 as 2. That is because we can have digits from 0 to 1, only 0 and 1, only two digits. We have to deal with only two digits in binary. This represents the circuit. That is, for sum, this sum refers to the equation sum is equal to A XOR B. And carry is equal to A and B. How do we decide it as A, B, carry? Based on the last output. The output of carry is high only when A and B is high, when both of them are high. So it is 1. So we have A and B, which is ANDed form. So we have AB. And coming to sum is, see, here we have A complement and B. B comp. This is A and this is B complement. A complement B plus A and B complement. This in turn this formula refers to this A XOR B. Okay, I hope you got a knowledge of sum and carry with respect to half adder, and this is the circuit how it looks. See, we are using OR gate. Since sum is A XOR B. A XOR B. And we are again taking the input, that is A, and here we are taking B, and we are ANDing it to get the carry, that is AB. Hope you all have got the idea about half adder. In the next slide, we have the behavioral coding style in Verilog. This half adder, I'm coding it in the behavioral modeling. That is, we have three models. The three ways of coding, that is behavioral, data flow, structural, and also we have something called a switch level. This is the exception case. We don't use it because it requires transistor switches. So we are not dealing with the switches. We only deal with these three: behavioral, data flow, and structural. Coming to behavioral, I have defined a module. Module represents starting of the lesson. And this represents HA refers to the name of the lesson. We can consider it as name of the lesson. This HA is name, something like name. For example, we want to represent half adder as HA. This is the name. And this module is like lesson 1. And this is representing it as a lesson 1. And this half adder is the name of the lesson. This is the example I can give. A, B, sum and carry. As we have seen in the last slide, A, B are inputs. Sum and carry are outputs. These are the ports which we define inside the module. And then again, we have A, comma B as input. We have to declare it as input. We have to let the code know what is input and what is output. So we are declaring it as input, that is A, comma B, and we are defining output, that is sum, comma carry. We are defining it as reg because, see, we have two types, wire and reg. By default, the wire value is Z, and this is X. By default, all the variables will have wire value. Okay, wire is nothing but passing the signal from destination A to destination B, just passing. But coming to reg, reg is something like a register. What does a register do? Stores data, right? It stores 1 bit of data. So we are using reg for sum and carry because we need to store the result in the sum and also we need to store the result in the carry. So we are defining reg for both sum and carry. Since we don't want to store any data here, we are just passing the inputs. We are not giving any register value there. Always at A or B. This A or B indicates the sensitivity. Always at A or B. What does A or B indicates? If there is any change in the input A or input B, then I should begin. Means what? I have given the inputs. Means what? There is some change. This is A input, this is B. There is some change. And when I go to 0, 1, again there is some change. Whenever the change happens, the sum should be calculated and the carry should be calculated. That is how this works. Always at this represents the sensitivity. You can also write it as star. Whenever you don't know what is the sensitivity, you can represent it as a star. Within begin end, we'll give the sum. What is the formula for sum? As we have seen in the back slide, sum is A XOR B, right? This cap is a symbol of XOR operation. So A XOR B. Carry is equal to A and B. As I said before, it is AB. Means what? A dot B. Dot represents what? And operation, which is AND. So we have given the formula to calculate this end and we are ending the module. So lesson 1 is completed. It is similar to completion of lesson 1. The end module represents the completion of lesson 1, like completion of half adder. This is the behavioral style of coding. This is the simplest way, and usually in industries, we deal in this way. Coming to data flow. Data flow is everything is same, but we don't use any always block. And here we are not assigning reg. In data flow, hello? Hello? Am I audible?
Yes,
Hello.
ma'am, you're audible.
Okay. Okay. So coming to output, sum and carry. You can
Yes,
see the
you are
difference that,
audible.
okay. So you can see the difference that I have written reg here in the previous slide. That is the behavioral style of coding. But in half adder, that to data flow level, I have not written reg because this assign represents the continuous assignment. In data flow, we'll use continuous assignment. Okay. And coming to this always block, this is a procedural assignment. This is a procedural. So whenever we define a procedural block, procedural means what? Always. Always at A or B or always at star. So whenever we define a procedural block, always the left-hand side, this is LHS part, right? The left-hand side should always be assigned by reg. Okay. But coming to this continuous, we'll have the sum and carry both as wires. Because as I said before, if we don't declare any reg with respect to any variables, by default, input or output might take wire as their data type. Okay. So here we are using assign. Assign is a continuous statement. Continuous statement actually tells that we are driving the signals continuously. Okay. But here we are actually not driving continuously. Whenever the input changes, we are getting the output, that is sum and carry. But here we are continuously driving. So we are not using any reg variable. Okay. Assign sum is equal to A XOR B. Assign carry is equal to A and B. I hope you know this formula for half adder. That is what we have written here. And this is the end of module. This complete refers to lesson 1. Means what? Module represents lesson 1. End of module represents the completion of lesson. And this HA is nothing but half adder. Half adder is the name. You can represent it anywhere. HA or just H or half adder. Anything. Okay. So this is data flow level modeling. In data flow, always will use continuous assignments. And coming to behavioral, we always use procedural. This procedural is very important because in industry, we usually use procedural assignments because this is the easiest way of coding. I'll let you know. Okay. Coming to structural. So what is structural? Structural is nothing but we use primitive gates. Primitive gates. What does primitive means? See, what does primitive means is XOR and AND. See, the module, input, output, both are same. Everything is same. Only these two are the differences we can observe in structural. See, here we can observe only assign statement as the difference. Here, XOR and AND is the difference, right? Primitive means we have inbuilt gates, which is inbuilt. For example, here we are using XOR gate and AND gate. This sum, just a minute. This sum is actually output, nothing but destination. This A comma B, these both are source. Source means what? Inputs. Okay. I think someone has turned on the video. Can you please turn it off? Yeah. Okay. Thank you. See, we have AND gate, OR gate, NOT gate, XOR, XNOR, NAND, etc. We have so many gates, right? All these gates are inbuilt in Verilog. We can use these gates and we can also get the output as similar to data flow and behavior. See, when coming to XOR, yeah. See, when coming to XOR, Coming to XOR, this is the destination. Destination indicates output. O means output. And this A comma B indicates source. Source is where you give the input, right? I means input. We are actually defining XOR operation of sum and carry. The sum and this AND operation of carry, right? We know that sum is equal to, yes, sum is equal to A XOR B, right? So we are using XOR gate, and this is the source and this is the destination. This automatically refers to this formula. Means what? This is the output, destination this is the destination, A comma B, this is the source. So we are indicating this complete formula using a single gate. This single gate primitive is nothing but XOR. This is the output and these two are the inputs. Similarly, AND gate. Coming to AND gate, we have, coming to AND gate, this is the destination. Destination indicates what? Output. Output. And this is, these two are source. Nothing but inputs, right? Coming to AND gate, this AND gate, we have formula for the half adder, that is carry is equal to A dot B, right? A dot B. By using this AND gate, we are indicating that this is the formula. What? This is the formula. So, which indicates, which redirects to this formula, that is A dot B, perform A dot B and store the result in carry, this carry, right? Similarly, in XOR also, we calculate sum and then we store the result in sum. That is how the structural level works. Hope you all got the point, whatever I said. Coming to full adder. In full adder, we have three inputs. Three inputs, two outputs. What are three inputs? A, B, and C. These three are the inputs. Sum and carry, these two are the outputs. Okay? So, 2
Before
power.
can I ask you a question?
Sure.
You show the three way of coding, right? But
Yeah.
where actually means what is the difference? Means why, in which situation we use these different type of coding basically?
Okay, based on your requirement, whether you want to deal with the gates, whether you want to use the structural, whether you want to use data flow, because sometimes you will use data flow. We have conditional operators as well. That actually will be more efficient when compared to procedural as well, because we use case statements. So based on our requirement, we'll be dealing with the behavioral or data flow or structural.
No, that's a what type of requirement? That's actually means yeah. Both all the same, right? But the way
Yeah.
of coding is different. So that's the
But
thing.
see,
Means,
behavioral is the easiest way of coding. So we usually choose behavioral. But coming to XOR, coming to structural, we'll have to use many gates.
that's the
If the design becomes more complex, then we have to use structural. That doesn't make a sense, because it takes a lot of time to use all the gates and to code all the gates. Rather than we can go with behavioral, we can just define the functionality within the always block.
Okay. Anyway, yeah. Another thing, this always is a loop, or is it a event driven means
It is an
event
event
capturing
driven,
function?
event capturing
Okay.
function. It
Okay.
is synthesizable. Can I move
Okay.
ahead?
Sure.
Okay. Okay, we have 2 power n is equal to question mark. Again, we have 3 inputs, so we have to take 2 power 3. As I said before, this 3 indicates the number of variables. So 2 power 3 is equal to 8, right? So we have three inputs, A, B, C in. These are the possible combinations. And this is the carry and this is the sum. So we have an equation for sum. That is, sum is equal to A XOR B XOR C in. And for carry, we have AB plus BC plus CA. This is actually C in, okay? C in is nothing but C. Since I'm using it C here, to get to know the difference, I'm writing it as C in, okay? So this is the formula. This is the basic circuit of full adder. As I said, sum is A XOR B XOR C in. So we are building a circuit. We are using three inputs. See, A, B. First, we are XORing these two. Since we are not using three input gates, we are using two input gates. And with the two input gates, we are using XOR gate. We are actually building XOR gate. And here we get the output as A XOR B. Here we got A XOR B. Then we are defining C in here. We are taking the C in here and we are connecting it here. Since we get the output as here, in this point, we are getting the output as A XOR B. While giving this C in here, the output can be A XOR B XOR C in. As you all know, carry is AB plus BC plus C in. CA, right? Okay, let's start with AB. This A they have taken, and this B they have taken. They have ANDed because we have AND operation in between these two, A and B. Coming to B and C. We can also write this as, okay, I'll write my own circuit because this is in another way. Okay, so you can write it as this is A and this is B. And we have C in here. We are XORing and we are getting the sum. And as I said, for carry, we have to take A, B, and AND it. And then B, C, AND it. And then we have to take this C and this CA because we have C in and A as ANDed, right? And then we have to OR it. This actually takes 3 input OR gate. So after simplifying all this, we'll get AB plus C in into A XOR B. So for this formula, they have written the circuit here. So this is with respect to, we have taken AB ANDed and then A XOR B with C in and it, and then we are ORing it. So we can get the carry. Okay. Coming to behavioral style of coding, full adder. We have three inputs and two outputs, that is sum and carry. Always at star. As I said before, when you don't know the sensitivity list, you can give star. We are beginning, and then S is equal to A XOR B XOR C. We are defining the formula as per the circuit, as per the diagram. And C out is A and B, or with A XOR B and its C. As I said, C is equal to A dot B plus C in into A XOR B. This is what they have written in this code. We can also define it in the way we defined earlier, that is C in is equal to AB plus BC plus, this is carry, C in plus C in into A. We can also use this formula. Either AB plus BC in plus C in A can be used here in the C out, or we can use this formula. This is with respect to behavioral. And coming to data flow, this is the parameterized full adder. For example, we want a 4-bit adder. So how do we define it? 4-bit adder, which adds 4 bits simultaneously. How does it do? So here we are defining the input as a vector. This itself is a vector. Why are we defining the parameter? I'll let you know later. Let us get to know about the input width minus 1 down to 0, A comma B. Actually, in place of width, we should write 4 minus 1 down to 0, or we can write it as 3 down to 0. Okay, this indicates what? 0 is the first bit, and 1 is the second bit, 2 is the third bit, and 3 is the fourth bit. So there are 4 bits here. This indicates 4 bits. This 3 is MSB, and this 0 is LSB. So what we are doing is, we are generalizing it by defining width. So whenever someone wants to change it to 5-bit adder, then he can just simply erase this 4, and he can write it as 5 here. Since we are defining it in general way, we are using width minus 1 down to 0. Means what? For example, I am a new user. I would like to get a 5-bit adder. So I'll write 5 as the width. Width is equal to 5. Then here internally what gets replaced with width is 5. 5 minus 1 down to 0. So I get 4 down to 0. As I said, 0 is the first bit, 1 second bit, 2 third bit, 4 is fourth bit, and 3 is fourth bit, and 4 is fifth bit. See, 0, 1, 2, 3, 4. We have from 0 to 4, right? This is the first bit, second bit, third, fourth, and fifth. So totally I get 5 bits, this 5. Okay. So that is why we'll give the width as a parameter. We are parameterizing it so that in general, we can declare, we can.
Yes, ma'am.
Fine. Okay. Okay. So as I was saying it before, that this width, you can give it as anything. See, if you feel like giving it as parameterized value, this is just a name. This parameter is a keyword indicating that this width is a parameter, which is generalized. Means what? You can change anything here. You can give it as 5, 6, 7, 8, whatever it is, you can give. And input width minus 1 down to 0. As I said, If I give it as 5, it becomes 5 minus 1 down to 0. That is 4 down to 0, which becomes 5 bit. Okay. Actually, you can write it as 3 down to 0 for 4 bits, or you can also write it as 0 down to 3. What is the difference? See, this 3 represents MSB. And this 0 represents LSB. But coming to the next one, this 0 is LSB. And this 0 is MSB. This is MSB. And this is LSB. Always the left-hand side. This is LHS, right? The left-hand side is always MSB. And the right-hand side is always LSB. So these two are the differences. We can either write in this way or this way. But we should know that which is LSB and which is MSB. Then we can deal. Okay. Output also we have done the same thing. What we have done? The sum can be of n number of width. But carry is only one bit. So we are not defining it as bit minus 1 down to 0. Something like that. We are not defining it because since it is a 1 bit. 1 bit stores only either 0 or 1. But this can hold 1 0 0 or 1 1 0, something like that. Sum and this input. We give these two as a parameterized variables. This is parameterized. So hope you all understood. Why do we use the parameters? Got it? Hello?
Yes, ma'am. Got it.
Okay. But coming to behavioral, see, here we are not defining any bits. For example, that is bit minus 1 down to, we are not parameterizing it. So it is a single bit, 1 bit operation. This is 1 bit addition. Okay. But here we are defining the width. So it can be a multiple bit operation. For example, I have taken it as a 4-bit adder. That is why I have given the width as 4. Hope you understand all this. And coming to this assign. So what it is happening is, for example, I have written this operator, this flower bracket indicates concatenation operator. So what I'm doing is basically I'm adding all this. I'm not writing any formula. For example, I'm not writing A or B, A XOR B XOR C as sum. And carry, for carry, we have AB plus BC plus CE. We don't write all this. We just use the simple expression, that is concatenation of C, that is C out, comma, S is equal to A plus B plus C. So which indicates what? Okay, which indicates what? Let us assume A is 1, 0, 0, 0, 0, 1, 1, 1. And okay, let us assume this. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 0. And 1 plus 0 is what? We have 1. Right? So we have totally 4 ones, which indicates 15. Nothing but F. And we have no carry. So carry is 0. This C is 0. Because we have not got any carry. And this 4 bits indicates sum. Right? So what I'm doing is I'm adding these 3 bits, that is C, A, B, C. I actually should had another one, that is scene. Scene, you can take any of the bits, 1, 0, 0, something like that. See, when you add all these 3, you should get carry. For example, let me add these 3 bits. This is A, and this is B, and this is C. Okay. 0, 0, 1 is 1. 0, 0, 1 is 1. 0, 0, 1 is 1. 1 plus 1 is 0. And we have 1 carry. Right? So whenever we get the carry, this gets stored in C0. And these 4 bits gets stored in where? Sum. This sum. Got it? So whenever we write A plus B plus C, we are getting the sum and storing it into this. Yes. And The carry is stored into this. See, here we have 1, 0, 1, 1, 1. This is 4-bit and this is one extra bit. Let us assume that I'm defining it as 4-bit. Since 4 minus 1 down to 0 is 4 bits, sum is 4 bits. So this 4 bits completely goes to yes. And this 1 bit is remaining. 1 bit refers to what? This carry. So this carry represents C0. And this one will go to C0 and get stored there. So this is one way of coding using the assign statement. This assign, as I said, it is a continuous assignment. And this is the structural full adder. What does structural full adder indicates is, see, here we are using module full adder, ABC, sum and carry. Inputs are ABC, output is sum and carry. I'm declaring it as wire. Even if you don't declare N1, N2, N3 as wire, it is fine. By default, if you use any of the variables, it takes it as wire itself. So this is not necessary. For your observation, you can write. Okay. So we are using two half adders to build a full adder circuit. So for example, just a minute. Okay, see. See, this is full adder, right? And we can build implementation of full adder using half adders. For full adder, we have 3 inputs. For half adder, we have 2 inputs. So what are we doing? We are using one full adder here. That is with inputs A and B. The sum we are giving it to next half adder. And with input as C in this one. And we get sum. Right? From here. Okay. From this output, we get A XOR B. And here we are passing what? C in. And what is the output that we get for sum? That is A XOR B XOR and C in. C out is, we are passing the C out here and we are getting the output from there also. And we are ORing it. And we are getting the C out. That is AB plus C in into A XOR B. So, okay. So with these two half adders, we can build full adder with the use of OR gate. This OR gate is necessary for getting the C out. C out is carry. Okay. So coming back to the presentation. Just a minute. Yeah, see here we have two half adders, right? HA is the half adder, name of the half adder. Initially, sorry, just a minute.
I
Yeah. Okay, see, what I have to declare initially is we have to define the functionality of half adder. What is the functionality of half adder? Sum is equal to X XOR with Y. I'm defining X and Y as the input. Okay, I'm defining X and Y both as the inputs, and S and C naught are the outputs. You can write it anyway. You can either write A comma B, X, Y, Z, anything. You can write anything. And in ports also, you can declare the input first or output first. Anything. You can declare anything, but you have to mention it properly while giving the input and output. That is while declaring the input and output. So this is the functionality of half adder, right? So I'm using the half adder. Initially, what I have done, I have coded the half adder module. And next, what I have done is I have used this half adder module here 2 times. Why I have to use 2 times is because, as I said, we have 2 half adders. So using these 2 half adders, we should get the output of full adder, right? So we are using 2 half adders and 1 OR gate. I'll show you. Just a minute. See, here, as I said, we have 2 half adders. This is 1 half adder and this is second half adder, and we have to use OR gate, this OR gate. So what are we doing? Here, here we are using 2 half adders, right? These 2 are the half adders and this is 1 OR gate. So we are using half adder module here. This half adder HA represents what? This module. I'm using this module. This module is what? Yeah. This is the module I'm using. Okay. This indicates I'm using this module. And this H1 indicates the name of the module. For example, actually we call these 2 are the instances. So we are giving the name of the instance as H1. You can give any instance. You can give the instance name as anything. You can either give HA1, X something. You can give anything. You can give whatever you want according to your convention. Okay. What I have defined is I have defined H1. This H1 is the name of the instance. N1, N2, A, B. This N1 and N2 are the wires. A, B both are the inputs. So what I'm doing is, instead of C0 and S, see, this should actually match with this. If I declare the inputs first, that is, if I declare X, Y as input here first, in the first itself, then I have to declare it here as A, B. Because I'm considering A, B as the input, I have to relate these 2 inputs to X, Y, Z, X, Y, right? X, Y. And we have another input also, that is C. But later in the next half adder, I have to use C, because see, this A, B and this N2 and this N1, coming to A, B, we have these 2 as inputs. N1, N2 are the wires. These 2 wires, for now, it indicates sum and carry. But these are just the wires. We are not indicating it as a sum or a carry. And coming to half adder 2, as I said before, this C is the input, right? And this is what the output we get. And we are passing this output as input to the next half adder. And we are getting N3 as output and sum as the output. This N3, for example, you should understand it as carry. This is just a wire, but you have to consider it as a carry. And this sum is the original sum. As I said, see, this sum, we are actually taking this S, right? This S, this as N1. I'll write it here so that you can understand. Yeah. Okay. I think I can. How do I write it? Okay, just a minute. Okay. Now, see, we are considering this as N1 and we are considering this as N2. Whenever we have the wires in between 2 combinational circuits, we have to take it as a wire because it is just passing the signal. It is not storing. That is why we are taking it as a wire. This is N2, okay? And this is N3. Now, just a minute. Now, as I said, A, comma B are the inputs, N2 and N1 are the output, right? How is N2 and N1 are the output? I'll show you. See, this N2 is the output of Cout, and this N1 is the output of sum, right? We are assuming it that these are sum and this is Cout, that is carry. So we are declaring it as N1 and N2 and A comma B. And coming to the next adder, that is half adder, next half adder, we have to give what? Yeah. For the next adder, we have inputs as N1, Cin, and the output as sum and N3. As I said, whenever we have combinational circuit, that is, whenever we have two combinational circuit, in between, if a wire is passing, then we have to take it as any of the variable. You can take it N1, N2, N3, W1, W2, X1, X2, anything. You can take any of the variables according to your convention. Okay? Yeah, that is why C is the input. C is what? Input. This Cin is the input for the next half adder. And we have N1 as the input for the next half adder. This is second half adder, right? For second half adder, we have Cin as the input and N1 as the input. So when we open this, Cin, this C representing is actually representing what? Cin. These two are the inputs, right? Yeah. These two are the inputs. And we are getting N3 and sum as output, right? So how is it? We are getting sum and N3 as the output. And then we are using one OR gate. This OR gate is what? See, here we have N2 as input to the OR gate, N3 as input to this OR gate, right? And we are ORing it and we are getting the output. This is Cout. So what it means, we are connecting N3 and N2 in terms of OR to get the Cout. That is why I have declared OR, that is O1 as the instance name and carry is the output, N3, N2. These two are the inputs. As I said, we can use the primitive, that is gate primitives earlier. So with respect to gate primitives, OR gate, this is the destination, this carry is the destination, N2, N3 are the sources. So sources means what? Inputs. Destination is what? Carry. I hope you understood this structural behavior of full adder. Next, we have two input mux. Yeah. Okay, this is the two input mux, right? This two input mux can have, see, from mux perspective, we have 2:1. This indicates what? Two inputs, single output, one output. Anytime, at any time, we have only one output, but we have multiple inputs. What is the mux definition? Is we have 2 power n inputs, n select lines, and one output. What does this select line is? What does that indicate? Here we are representing the select line. See, for example, let me consider 2:1. 2:1 mux. What this 2:1 mux is? 2 power 1 indicates what? One select line. This, as I said, this n is what? Select line, right? So this 1 is select line. This 2 indicates inputs. Okay? And this 1 indicates what? Output. So what I'm doing, if this is the mux, these two are the inputs. One is the select line and one is the output. For example, this is A input, this is B input, this is the select line input, and this is output Y. Okay. So what it is? So whenever, okay, the output is equal to question mark. How does it work? Since based on the select line, the mux will work. Here we have 1 bit select line, only 1 bit. Indicates what? Either it can take 0 or it can take 1. Whenever the select line is 0, it will select A because we have something like 0 and 1 inside the mux, which indicates 0. This 0th bit indicates it is selecting A as input. And if the select line becomes 1, this indicates B as the input. It is taking B and it is passing this to Y. Okay. Yeah. So this is A. This is B. This is select line yes. This is Y. This is 2:1 mux. Okay. Now I'll write the inputs. That is just a minute. Yeah. Okay, I'll write it here. Select line and Y. Okay, we are not considering these two A and B as inputs because I'll show you. See, for select line 0, we'll get the output as A because this one is selected. As I said, when in the select line we get 0 as input, this indicates what? You select 0. In 0, what we have? We have A as the input. Then I'm directing this A to Y. Indicates what? For 0, I'll get A, and for 1, I'll get B. Because when I get select line as 1, I have to map this to B because B indicates 1, right? Then it redirects to Y. Okay. So this is actually the truth table, and the formula you can consider is Y is equal to S bar A plus S B. Okay, why S bar A? Because see, this select line is 0. 0 indicates what? S bar. And A is again the input which is given, right? And coming to the second one, that is SB, this S indicates what? This one, this input. It is 1. So we are not complementing it. We are not representing it as a complement. And since we are writing in SOP form, we'll consider 0 as A bar and 1 as A. Okay, that is why, see, for 0, we are considering it as S bar. And for 1, we are considering it as yes. So this is the formula for mux. Now we'll understand the Verilog code for mux. Okay, for mux, we have 2 inputs. As I said, these 2. And with the select line as another input. This is the special input. Okay, because based on the select line, we'll get the output. And this is output Y. That is Y. See, all these are 1 bit, single bit. I have not defined it as a parameterized variable. That is why it is 1 bit. By default, all these are wires. Even if I don't declare it as a wire, it will still become wire. Okay. See, I have not declared the reg here. I can declare it outside also. In the next line, I can say it as reg Y. Even this is okay. Or you can directly take it as output reg Y. This is also possible. This is also possible. These two are also possible. Okay. Now we are defining the functionality. What is the functionality? Is always at A or B or select line. See, as I said, this is the sensitivity A or B or select line, right? So whenever any of them changes, then what I have to do is I have to check for certain conditions. What I have to check? I have to check if select line is 0. What I said, if the select line is 0, y will become what? A, right? So what I'm writing it, if select line is equal to 0, then y is equal to A. That is what I'm declaring. Else condition is what? Else. If select line becomes 1, y is equal to B. This is the else condition, y is equal to B, right? This else will indicate S is equal to 1 because I have already taken this as select line 0. This else condition will indicate what? S is equal to 1 because we have only two possible cases, that is S is equal to 0 and S is equal to 1. Fine. So this is with respect to mux 2 cross 1. And this is the alternate method. Okay. This is the conditional operator. Everything is same. Everything is same, but only this. See, here we have 4 lines of code to define the functionality of mux. But here we have a single line which defines the functionality. Only single line, right? Single line. So what this indicates is y. Y is the output. I'm assigning what? Select question mark. This is actually a conditional operator. So what this indicates is, just a minute. Yeah. What this indicates is whenever the select line is 1, if this is 1, you select B. Okay. If this is 1, you select B. Or else, this is or else. This is like else condition. Else you select A. This select, for now, it indicates 1. Okay. So what I'm doing is y is equal to select question mark B or A. Means what? If S is equal to 1, then you select B. And then by selecting B, assign it to Y. Or else, if S is equal to 0, then what should you do? You should assign A as the output to Y. That is what it is doing here. Okay, it is like if-else condition, but we are writing in a conditional operator way. It is also called as a ternary operator. Okay. And coming to 4 cross 1 mux. As I said, in multiplexer, we have only single output. Here we have 4 inputs and 2 select lines and 1 output. So how is it 2 select lines? As I said, 2 power n inputs, 1 output, and n select lines, right? So 2 power 2. 2 power 2 is equal to 4, right? So we have 4 inputs. This 2 indicates what? Select lines. And this 1 indicates what? Output. Hope you understood. So we have the functionality that has select line, S0, S1, and this is Y. Okay. So when we have 0, 0, we'll select D0, 0, 1, 1, 0, 1, 1, D1, D2, D3. You can take anything. You can take it as A, B, C, anything. D, anything. But I'm taking it as D0, D1, D2, D3, D4, something like that. Okay, D0 to D3. So for this, we have the output. Y is equal to S0 bar, S1 bar, D0 plus S0 bar, S1, D1 plus S0 S1 bar D2 plus S0 S1 D3. This is the output that we get from the truth table. Just a minute. Okay. So this is the output that we get. Yeah. So coming to this code, here what we are doing is we are defining a vector 3 down to 0. So what we are doing is we are actually not using A, B, C, D. We are using only D and we are taking it as a D0, D1, D2 and D3. For that we are defining a vector. This data has a 4-bit value. This data is of 4 bits. Means what? 4 bits. 4 bits represent what? These 4 bits. And the input is select line. Select line is 2 bits, right? As I said, see, the select line is 2 bits. So we are taking 2 bits as select line. We are not taking it as S0 and S1. We are just taking it as select. Output is Y. Always at data or select. If select line is 2 tick P 0 0. I said, right? For 0 0 condition, it will select D0. Right? So if select line is 2 tick P 0 0 means what? If the select line is 0 0, then I am giving the data D0. This D0 indicates data of 0. Data of 0. This is the vector representation, which is equal to this one, this D0. Okay. And then else if select line is 0 1, then the data is 1. And if the select line is 1 0, then the data is 2. If the select line is 1 1, then the data is 3. This 3 data indicates what? D0, D1, D2, D3. But here we are not using A, B, C, D. We are directly defining it as a vector. Vector means multiple bits. Vector means what? Multiple bits. We can define multiple bits. Okay. Yeah, this is an alternate method using the case statement. We have something like case. That was using if else, but this is using case statement. This case should have some sensitivity. That sensitivity is select line, because based on the select line, the input gets selected and assigns to output, right? So if we have 0 0, this 0 indicates what? This is 2 tick P 0 0 only, because the select line itself is a case sensitive. I mean, the sensitivity is here. The case sensitivity is select line. Select line has 2 bits, right? 2 bits. That is what? 4 combinations. That is 0 0, 0 1, 1 0, and 1 1. Right? Yeah. For this 0, this is actually indicating this 0 0. And this one is actually indicating this one. And this 2 is actually representing what? 1 0. And this 2 tick B 1 1 is actually indicating what? 1 1. You can either write it as 0 1 2 3, or you can write it in this way also. And whenever this is the case, yeah, whenever 0 is the case, 0 is indicating what? 0 0. Whenever the select line is 0 0, what I'm doing, I'm assigning the data D0 to Y. So whenever it is 0 1, I'm assigning data 1, that is D1 to Y. Whenever it is 2, that is 1 0, I'm assigning data 2 to Y. Whenever it is 1 1, it is 3, right? 1 1 represents 3. So that indicates I'm sending the data, I'm assigning the data D3 to Y. Default condition is Y is equal to 1 tick BX. Means what? If I don't get any of these values, for example, if I don't get any of these values, 0 1 0 1 0 1 1, if I get some X value, then it will come out of the case statement and it will assign the default statement. That is Y becomes equal to 1 tick BX. And then we are ending the case end module. This case is used. The controlling expression select line and each alternative 0 1 2 3 are compared bit by bit. The first successful match causes the associated statements to be evaluated, right? Because see, with respect to these inputs only, they get assigned. The data get assigned to Y. But whenever I get value something like X or Z, these are the out of box conditions. These are not with respect to select line. So then the Y value becomes X, that is one tick BX. Hope you understood this way as well. And this logic gate, this is a logic gate, not gate is a logic gate. Using mux, we can develop using a mux. So initially, what we know is this is the representation of NOT gate, right? A here.
Excuse me.
Yeah, tell me.
Yeah, here we are writing like 4x1 mux for the 4 cases, right? Like 0, 0, 0, 1, 1, 0, and 1, 1. Okay, what is the purpose
Yeah.
of writing this default condition? If we don't write, like what will happen?
Yeah, we'll get the latch inferred because will not be given the conditions for if at all we get any X or Z. If at all we get any X or Z value, then what happens? It might not get assigned with any of the values, right? That is why we have to write the default condition.
Okay. Okay, ma'am.
Yeah. And coming to this is a NOT gate. This is a basic NOT gate. This is A bar, right? So what we have to do is we have to develop a NOT gate using mux. Which mux? 2 cross 1 mux. That is 2 input, 1 output, and 1 select line. So how do we define? First, we have to get the truth table. What is truth table? That is A input and Y as output, right? For 0, we'll get 1, and for 1, we'll get 0. This is the truth table for NOT gate. Now, what we have to do is, see, always the first input becomes the select line. Okay. Why is it so? Because since we have only 1 bit here, and this represents 0 or 1, right? For first case, it will become 1. For first case, it will become 0. In the next case, it might become 1. Since it is a 1 bit, we are taking select line as A. And then, so if we take select line as A, we might get it as 0 or 1. So whenever A is 0, what should we get? We should get the output as 1, right? Y should be 1. So what do we have to pass? So whenever A is 0, it selects this one, right? This one. So since it selects 0th line, it indicates what? I should give it 1 here. I should give 1 as the input so that whenever A is 0, it will direct to this line, this input, and this is assigned to Y. So Y becomes what? Y is equal to 1 whenever A is 0, right? And whenever A is 1, what should happen? Just a minute. Yeah. Whenever A is 1, what should happen? Y should get 0. Output of Y should explain through this. Just a minute. Okay. This is the NOT gate. This is input A. Y is equal to A bar. This is the output of NOT gate. And we have the truth table. That is A is input and Y as the output. So whenever A is 0, output is 1. Whenever A is 1, output is 0. And when we want to design mux, yeah. So when we want to design a mux, which is of 2 cross 1, right? 2 cross 1 mux. We have 2 inputs, 1 select line and 1 output, right? So what I have to do is I have to take A as select line, A, and this Y as the output. Now, here we should decide what are the inputs we have to give. Okay. First, I'm giving the input as 1 and 0. Why am I giving this 1 as the input to the first line? Is because, see, whenever whenever A is equal to 0, Y should get the output as 1, right? So if A is 0, it is selecting the 0th line. This 0th line. This 0th line has what? 1. So I'm giving the input as 1. So what it is doing? So it is selecting 0th line. In 0th line, it has the input as 1. Then it is redirecting to Y and assigning Y is equal to 1. Okay. And now, yeah. Now, whenever A is equal to 1, what should happen? Whenever A is equal to 1, Y should be getting the value of 0, right? So if the select line A has the value 1, if this is 1, what it is doing? It is selecting the first line. In the first line, what do we have to give? We have to give it as 0 because see, as I said, whenever select line is 1, the output Y should be getting what? 0 as the output. So whenever A is 1, the select line A is 1, it is redirecting this to 0. That is first line. In the first line, we have 0 as the input, so it is redirecting this to Y, and Y becomes equal to 0. So totally, the circuit looks, just a minute. Yeah. So totally, this is the circuit for NOT gate using MUX. Okay. So that is what I have defined here. So this is actually the circuit for NOT gate. Okay. Then now we are defining the Verilog code for this gate, that is NOT gate, using MUX. First, I have to define the MUX Verilog code, right? So I'm taking two inputs, that is I0 and I1, yes, comma, Y as the output. Input I0, I1, yes, sorry, the select line is the input, okay? Y is the output. So what I'm doing, whenever it is 0, I'm taking I0 as the output. Whenever it is 1, then the select line is 1, taking I1. I'm displaying the default statement as error, something like I'm not assigning a value, I'm just displaying it to display an error. And then I'm ending the case. This complete code is with respect to MUX. First, I have to define the functionality of MUX. Then I have to define the functionality of NOT gate using MUX. So what I have to do, not using MUX, right? We have one input and one output, right? A is input and Y as output. So what I'm doing, input A, output Y. MUX 2 cross 1. So what is this? This indicates the instance, that is the name, right? S0 indicates the instance name. You can give it as anything, M1, M2, M3, M0, anything. S0, S1, anything, okay? So what I'm doing is, instead of this I0, I'm assigning one tick B1. This one tick B1 is what? 1. This is actually I0, okay? And this is actually I1. So instead of I0, what I'm assigning 1 because I'm giving the value as 1 for I0 value, okay? And for I1, what I'm giving the 0, this 0. So I'm giving the 0, that is one tick B0, comma, A as input, because select line is input, right? Here, it was a select line. So instead of select line, what I gave, S is equal to A. So I have given the select line as A. So I'm declaring the A here. And same Y as the output. Okay. And that is how the circuit works with respect to NOT gate. And this is AND gate using MUX. I'll show you. Yeah, we have AND gate. So this is the AND gate, A and B. This is Y, right? So first we have to write the truth table, that is A, B. These two are the inputs, right? And this Y is the output. 0, 0, 0, 1, 1, 0, and 1, 1. Okay. And what is the output? 0 into 0, 0, 0, 0, and 1. Okay. Now we have to design this AND gate using mux. That too 2 cross 1 mux, right? So what I'll do is, okay, I'll write it here. This is 2 cross 1 mux. We will have 2 inputs, 1 select line and 1 output Y. Okay. As I said before, always the first input is taken as select line, always. So we'll take A as select line because see, we have 0 combination and 1 combination. It is not changing from 0 to 1. It is taking 0 values and then 1 values. It is not changing. That is why we are taking the select line as A. Always the first input must be taken as A. That is select line. The select line should be A always. Okay. Now we have to get the value of Y. So what is the value of Y? How do we get it? Since we have 2 inputs, only 2 inputs, we have to group these 4. I mean, these 2, which has 4 combinations, these 2 into 2 groups. That is, see, we have to group these 2, that is these 2 and these 2. So how is it? See, for the first group, for this group, what I'm doing is, I'm checking that whether B and Y are same. That is, see, for 0 or 1, we are getting the output as same. That is 0 itself. Means what? Even if the B is 0 or 1, the output is 0, right? So what I have to write? I have to write as 0 here because whenever the A is 0, if the select line A is 0, and if the B value is again 0, I will still get the value as 0, right? And if the select line A is 0 and the B is 1, I will still get the value as 0. So I'm taking it as 0. Okay. Yeah. And coming to next, this combination. So for this combination, these 2 combination, what I'll do is, I'll have to check between B and Y. See, if B is 0, Y is 0. If B is 1, Y is 1. Means what? B itself. Because, see, whatever is the B, Y is getting the same value, right? That is why I will declare it as B here. That is, A is the select line. B is what? B is input. And 0 is also input and Y is the output. Now, we'll check. Okay. For A is equal to 0, for A is equal to 0, what should I get? I should get Y is equal to 0. We'll check whether it is working or not. For A is equal to 0, we are mapping the first line, that is 0th line, right? In 0th line, what we have? We have 0. So we are getting Y as 0. So we are getting Y as 0. And for next combination, that is for A is equal to 1, we should get Y is equal to what? B value. B value is what? 0, 1, 0, 1. Same, right? That is why I have considered it as B, right? So I should get B value. We'll check. If A is equal to 1, whether I'm getting B value or not. See, if A is equal to 1, it will select first line. In the first line, we will have B as input. So it is redirecting it to Y. So Y is equal to B. Okay, I hope you understood this concept. And this is the hello. Hello.
You are audible, ma'am.
Yeah, okay. Don't just see the circuit. They have considered B as, something, and they have ignored B. They have used the select line A. So they have used the select line S. Don't consider this. So whatever the circuit I have drawn here, that is just a minute. I'll draw it. Yeah. Yeah. So this is 0, and this is B, this is A, this is Y. So this is what the circuit you have to consider. Okay. So coming to module, see, what we are doing, we are first initializing mux 2x1. We are declaring mux 2x1. That is, we are declaring the functionality, and then we are using mux to define the AND gate. So what we are doing is, see, in place of I0, we are giving one tick B0. Means what? See, this is I0, right? In place of I0, what we are giving the input as 0. And in place of I1, we are giving the input as B. Okay. So in place of I1, we are giving B. And the A is the select line, right? In place of yes, we are giving what? A. A is the select line. And in place of Y, we are giving Y as the output. Okay. So this is with respect to AND gate. Next, we have OR gate. So again, yeah. So what is the gate representation of OR gate? OR gate is, right? This is A, this is B, and this is Y. So A, B, first we have to define truth table always. And this is Y. 0, 0, 0, 1, 1, 0, 1, and 1, right? We all know that whenever one of the input is high, the output is high. Okay, so one of the input is high, one of the input is high, both the inputs are high. Okay, then now we will draw mux. We'll draw a mux, which has two inputs because we are using 2x1, right? And select line 1. Output is 1. This is I0 and this is I1. We are just defining it as name, the name of the lines, this line. Okay. Now, what I said before is we have to consider this A as select line always. Okay. And now we have to take these two combination. Okay, and these two combinations. Now we have to define the output. So what do we have to do is, see, for this, what we have to do is we have to check for this one. Okay. See, whenever B is 0 or 1, what I'm getting? Y is equal to 0 or 1 means what? Whatever it is, whatever the value of B, the same I'm getting at the output side. So I'm declaring it as B. And whenever, in the next condition, whenever B is 0 or 1, the output is what? 1. So I'm declaring it as 1. See, even if the B changes, the output is still 1. Okay. So this is the circuit for OR gate. The same you can build for all the logic gates and universal gates. Okay. So initially what we are doing, we are defining the module for mux 2x1. We are sorry. No. Dollars display is actually, it is, it's a method to display.
Okay, like print, ma'am.
Yeah, it is. It's like completely like print. Yeah.
Print. Okay.
Yeah.
Ma'am, why do you not use always in structural coding, ma'am?
Because see, in the structural, we have to, okay, see. Here we have something like this, right? This circuit. This circuit has two AND gates, one OR gate and one NOT gate. Here we have to use 4 logic gates to build this circuit. But instead, if we don't use the structural way, it is easy, right? Using if-else condition, we just have 4 lines. Here we have to analyze the functionality for each of the gate and we have to define. For example, see here in the OR gate, we have to define the destination and source, right? Here we have 4 gates. So we have to define the functionality of each of them and we have to right? We have to assign the value to them and we have to get the output. Rather than this if else is very easy, right? And it is easily understandable by anyone when compared to this OR gate, right? Can you understand this? If you don't know the circuit, can you understand? This is not possible because you might not be knowing what the circuit is and how the circuit works, right? But if you just see this, okay, you'll get to know, okay, when select line is 0, the output is A, and when select line is 1, the output is B. That is how it works, okay?
Yes, ma'am. But my question is why we not use always and register in structural coding, ma'am? Structural model.
Structural, okay. See, actually, we are not triggering any event there. We are not triggering like this. We are not just triggering. We are just passing the inputs like signals. We are not assigning. We are not, we are not taking it as a register. We are just passing the signals. Where is it? Just a minute. I'll show in the half adder. See, here it is taking it as a wire itself. A comma B, it will get the output, and A comma B, it will get the output. This is actually the pre-implemented method to define the structural, to define the data flow, to define the behavioral. Okay, this is the correct way of defining them. This is like the basic syntax. That is how we usually follow. Okay.
Okay, ma'am.
Ma'am, please show the last slide.
Okay, okay. Yeah. Don't consider this circuit. This is not related to this, okay? For your reference, I can share the PPT as well, okay?
Anyone have any doubts? Anyone have any doubts? So should we end the meeting?
Yes,
And
sir.
also, I have a suggestion for you all.
Yeah.
I have a suggestion for you all. See, always, whenever you code Verilog, System Verilog, or UVM, always use GVim. This is a Vim editor. Just a minute. Yeah, this is a Vim editor. This is very useful in coding Verilog or System Verilog or UVM, any of the scripting, okay? Hardware languages. This is very important. You should learn this
You can
GVM.
start with anyone, but after the whenever we have the huge codes, then GVim or some editor is useful, obviously. Right.
Yeah.
Initially, they
GVM
can
is very,
use
very
anyone.
useful.
Yeah, initially they can use anything, right? For the basic.
Yeah, they can use anything, but if they start using GVim, they
Yeah.
can understand the logics very well, and they can understand the flow of using GVim very well.
Okay, yeah, exactly.
That is why I suggest them to use GVim, because in industry, we usually deal with GVim. We deal with GVim and we code very faster, in a very faster manner. That saves the time. So always code using GVim. I will also help you. If there are any questions, I can help you out. You guys can reach me out. Okay.
Okay, ma'am. Thank you, ma'am. Thank you, everyone. Thank you, guys. Thank you so much.
Okay. Bye-bye. Take care.
Thank you.